In this example, we have two charges that are 1.60 meters apart from each other. The charges are given there on the diagram. And the question is, what's the electric field at the midpoint between the two charges? Well, the electric field at any given point is simply the vector sum of the electric fields from every charge in the region. So let's take the two charges that are in the diagram, calculate the electric field for each, and then sum them up. Let's start with a positive charge. We'll call the electric field from the positive charge E1. The field is given by E1 equals kq over r squared. K is 9.0 times 10 to the 9 Newton meter squared per coulomb squared. Q, the value of the charge, is 0.60 coulombs. And the distance from the charge to the point we are interested in is 0.80 meters. If the charges are 1.60 meters apart from each other, the midpoint is 0.80 meters from each charge. The meters squared cancel, and one of the coulombs cancel. That gives us E1 equals 8.4 times 10 to the 9th newtons per coulomb. That's the electric field coming from the positive charge in the diagram. Now let's move to the negative charge. We'll call that charge's electric field E2, and it's given by E2 equals kq over r squared. K is 9.0 times 10 to the 9th Newton meter squared per coulomb squared. The charge of this charge is 0.30, and it is also 0.80 meters away from the point we're interested in. Once again, meters squared cancel and one of the coulombs cancel, so E2 is 4.2 times 10 to the 9 newtons per coulomb. Alright, now we have the electric fields from each charge in the diagram. To get the total electric field at the point we're interested in, we have to add them together as vectors. To do that, we have to get direction. How do we determine direction? Well, let's look at the diagram. Positive charges always have electric fields that point directly away from them. So at the point we're interested in, the positive charge's electric field will be pointed directly to the right. So its 8.4 times 10 to the 9th newtons per coulomb field is pointed to the right. The electric field from the negative charge is also pointed to the right because negative charges have electric fields that are pointed directly at them. At the point we're interested in, that means the electric field from the negative charge has to point to the right, so it points directly at the negative charge. So the negative charge's 4.2 times 10 to the 9th newtons per coulomb electric field points directly to the right as well. Now we can simply add these two electric fields as vectors. They're both pointed to the right, so we'll call them both positive. So the total electric field is simply E1 plus E2. E1 is 8.4 times 10 to the 9th newtons per coulomb. E2 is 4.2 times 10 to the 9th newtons per coulomb. They're both positive, so we just add them together. So the total electric field is 1.26 times 10 to the 10th newtons per coulomb. Notice that since we're adding here, we look at the precision of the numbers. Each of these numbers go out to the 0.1 times 10 to the 9th place, so the final answer has to go out to the 0.1 times 10 to the 9th place, which is the same as the 0.01 times 10 to the 10th place. What about direction? Well, the value is positive, and positive means to the right, so the total electric field is 1.26 times 10 to the 10th newtons per coulomb to the right. Now, I'm not going to go through the next part of the example with you, because it's pretty straightforward. You will take this answer and you will use it in that part of the example, but it's pretty easy, so I'm not going to go through it here.